Kevin, what would you like to talk about today?
Um, I'm interested in the Heisenberg uncertainty principle. I think it's thrown around a lot in mass media, but I'm not really sure what it is, and we're learning about it in this course.
Okay. Um, Kevin, do you believe in the law of conservation of mass?
I would like to believe I do. I haven't experienced anything that or learned anything that would contradict it otherwise.
So, if you believe in the law of conservation of mass, what about like conservation of momentum? Do you believe in that?
In momentum, just as like the physics momentum
Yeah,
where
exactly. Yeah.
things just keep moving or
Yep. Yeah.
just don't
Or
move.
exactly. Or if one object collides with another object, the total amount of momentum will be conserved, right? So if you take a big object and it slams into a little object, the little object is probably going to move off, take some of the energy and move off pretty rapidly, right? So do you believe in that?
Yeah, I've played pool before. I think it works.
Exactly. If you played pool, you've done that. If you've been playing soccer and you get hit unexpectedly by the ball in the back of the head or something like that, you know, right? You know. And I think that the Heisenberg uncertainty principle is basically the law of conservation of momentum, but we don't think about it in that in the same way. So if you imagine like a car driving down the street in front of your house, and for some reason somebody lobs a tennis ball at the car, and you believe in the law of conservation of momentum, you know that, hey, if that tennis ball hits the moving car, okay, doesn't really matter very much, right? The ball will bounce off the car. Might or might not, you might not even notice that there's some change to the direction or the forces of be acting on the car. And that's because you got a little tiny ball hitting quite a big car. But if you imagine at an intersection, you have a car rolling down the road, and instead of throwing a tennis ball at the car, you throw another car drives into it. You know that the car that is hit is going to veer off of its original path, right? I don't have to convince you. That I don't think is a difficult thing to convince you of. All right, so now Heisenberg uncertainty principle says that when you are trying to understand some object, and in our case, those objects are electrons, and they're really small. Mm-hmm. And so if you imagine the electron as being small, and you're trying to understand where that electron is moving along in space, and somehow you have to detect it. Well, that means that you've got the electron is this little car that's driving through space, and you're lobbing at it not a tennis ball, but you're lobbing at it another photon or another electron, right? And so as that electron is moving through space, all of a sudden this other photon comes in and whacks it. Well, if you believe that they're of a similar scale, it's like a car at an intersection, right? And so when the detection device hits the thing that you're trying to understand, if they're both about the same size, then there's going to be some deflection of the path of the car going through the intersection. And so the Heisenberg uncertainty principle says basically that in our way of trying to understand that where electrons are and how they're moving, we can't both know where it is and detect where it is, because in the act of detecting it, we have changed it somehow. And so we cannot, so the uncertainty principle says we can know where it is right now, but we won't know how it's moving, because where it is right now is how it got to where it is right now is not going to be where it is, because we're going to change it by the act of detecting it. And so we can't know where the electron is going if we know where it is. And if we know where it's going, we can't detect where it is right now, so to speak. And so that is my way of trying to understand Heisenberg uncertainty principle, is that we've got these objects that are small, and the things that we detect them with are about the same as the size as the thing that we are trying to detect. And so they interact with each other, and so we don't get back the kind of information that would tell us both position and movement for the electrons. How does that sound to you?
That's pretty interesting. I've never heard it explained like that. So it's basically because we're driving another car right into that small electron car. And not only that, when you think of a car in an intersection, it seems to be going at a pretty normal speed, but with the electrons, it's as if it's going 100 or 1,000 times faster than a car normally would, because it has so much energy in it. It's so much smaller, the scale. Because even when you get a car crash, right, if you had a camera at that intersection, you'd be able to determine how fast the car was when it gets hit or when it's speeding off, veering off. But the electrons are just so much faster than that. We were unable to know how fast it is when we detect where it is.
Right. I mean, even when on our macroscopic scale, when you take a picture of a car crash or the film of a car crash, the event is bombarded by those photons, right? And they have mass, and so they are changing the actual crash as you're trying to detect them. Just so happens that in this case, the masses are so different that we assume that car crash happened exactly the way we filmed it, because the photons that were used to detect the crash had a minuscule impact on it. But when we're talking about atomic level, electron level events, the photons and the electrons and the electromagnetic radiation that is used to detect those events is actually very big compared to the actual event. So it's kind of like you're trying to detect a car crash by throwing dynamite underneath the car or something like that. I don't know. I'm not sure that analogy works, but the scale is, when the scales are the same, or the scale and the order of operations and the magnitude are close to being the same, the detection has an impact on the event itself. And so that's why we can't know those things simultaneously. At least that's the way I understand it.
Yeah, I think that's pretty interesting, because as chemists, we just want to know so much more about electrons, but if we can't figure out where it is and how fast it's going at the same time, it seems like a little block, but
yeah,
maybe.
I think it's a scale problem equivalent to absolute zero temperature, right? If temperature is the movement of electrons and 0 degrees Kelvin is when you have no movement, then you can't detect the temperature, right? And so that's why it's a big deal when people get to within 1/10 of a degree or 100th of a degree of absolute zero or 1,000th of a degree of absolute zero, because you cannot get to zero, because as soon as you have no molecular movement, then you're not really measuring temperature anymore. You're measuring, I don't know, I can't comprehend it. But it's this a similar logistical problem.
Is that all for Heisenberg then?
That's all I got for Heisenberg. That's all I got for it. Yep.
All right. Thank you, Dr. Hunter.
Thank you, Kevin.